Hey everybody, this is Mr. Schaefer, and I wanted to take you through some notes for today on polynomial functions. We're going to spend about 2 days looking at polynomials, and I'd like to show you just sort of an introduction background to how they work and some of the topics and key features that we're going to talk about in the couple days that we have ahead of us. So here's our Canvas page, and students, we're going to navigate down here to where it says 2.2 polynomials notes packet. It's that document that I'd like to have you look at with me here in this video today. The homework assignment for next time will be the polynomial worksheet. That's also a packet of about 11 questions. I'd like you to do 1 through 4 for homework, and you can see the answer keys to both the note packet and the homework packet are listed for you here. Let's dive in. We're going to study polynomials in this unit, and to start off with, a couple just definitions or characteristics of polynomials. We know them as functions that basically consist of a collection of terms, and the terms just are powers. They're kind of strung together. So something like 3x to the 4th minus 7x cubed plus 1x squared minus 18x plus 5. There's a polynomial. It has 5 terms. It's a degree 4 polynomial. We call that a quartic, because it's the highest degree, the highest exponent. And so we separate the terms with pluses and minuses. A couple sentences here. The domain of a polynomial, we'll start with that, is going to be all real numbers. Now the graph of polynomial functions you're going to see will be continuous. That means there's no breaks, there's no gaps, there's no holes, there's no asymptotes in the function. And it also has smooth, rounded turns. So there's no sharp corners, or in calculus we use the word cusps. So no corners or cusps. Like the absolute value graph has a sharp corner. That is not a polynomial. Okay, so a couple examples. Number 1, here again is a quartic, a degree 4 polynomial. So I'll call that 4. We'll write down the word quartic. A degree 2 is quadratic. Degree 3 is cubic. But the highest degree that I see here, the highest exponent, is the power of 4. So it's going to be a degree 4 polynomial. The leading coefficient is this guy right in front, the number 2, the multiplier in front of that power with the highest exponent. And then the zeros are the x-intercepts of my function. So let's go to the picture and try to pinpoint the zeros. Looks like there's 1, 2, 3, and 4 total zeros. So we'll write them down: -6, -4, +1/2, +2. And the y-intercept would be right about there at 50. Watch the scale. The number of local extrema, so that would be minimum points and maximum points. So the extreme values of the polynomial. And I see those right there is a minimum, there's a maximum, and here's another minimum. So it looks like a total of 3. 3 extrema altogether. Now, end behavior, that is an idea that we're going to talk about and maybe even look at a few videos. But end behavior basically just says, as I travel forever here, x goes to infinity, that's to the right. As I travel forever to the right, that means when I go this way across my polynomial function, or if there's a little hiker or a walker kind of traveling along my function and he's always going to the right, is the function climbing forever or is it falling forever? Is it increasing or is it decreasing? Well, here, if you imagine our little stick figure hiker or walker, as he travels always to the right, he's going to be climbing up that right end of the polynomial toward positive infinity. So we would say that the end behavior as x approaches infinity, as we go to the right, is also positive infinity here in the y direction. We're traveling up forever to infinity. What about if we went the opposite direction? What if the little hiker starts to travel to the left? As x approaches negative infinity, that would be the left side of things. So now think about going this direction. Well, if my hiker is right here on the graph and kind of walking along to the left forever and ever and ever and ever and ever, he is climbing once again. So he is approaching positive infinity. And what we kind of see here with this quartic is that the end behavior is up, increasing on either side of positive and negative infinity. Now the factors. For the factors, we want to go back to the zeros. The zeros are up here, so the factors would be x. If negative 6 is a 0, then x plus 6 must be a factor. And then if negative 4 is a 0, then x plus 4 must be a factor. Because if I set those factors equal to 0 and solve, I need to get the 0 that I started with. 1/2 is a little bit trickier. So if I think of x minus 1/2, what I really want to do is get rid of that denominator. So what if I multiply that by the 2? Distribute here. We'll get a 2x minus 1. And that's actually maybe a better factor for us to write down here for that 1/2. So 2x minus 1. You can check that. If you set that equal to 0, we should still get positive 1/2. And then finally, positive 2 is a 0, so there's my last factor of x minus 2. This is called factored form of the polynomial. Okay, some more with end behavior. So if the leading coefficient is positive, then what we're going to see is as the function approaches infinity to the right, then it's going to be climbing to the right. But if the leading coefficient is negative, then it's going to be falling. And an example would be, think about x to the third versus negative x to the third. X to the third is going to look something like that. Well, actually, it'll be going through the origin. But it's forever climbing toward positive infinity. Negative x to the third will reflect that, or flip the graph. So we'll start high and we'll fall down low to the right. So I'm overall falling down to negative infinity. If the degree of the polynomial is odd, like a cubic, then the end behaviors go in opposite directions. So we have sort of this down-up or up-down feature. But if the degree is even, then the end behaviors go in the same direction. So think of a quadratic. A parabola goes up, up, or it could go down, down. A degree 4 will have a little extra wave in it, like this, or down, down, like that. So even degrees go the same direction, up, up, or down, down. Odd degrees, like the cubic or the quintic, degree 5, they would go in opposite directions, up, down, or down, up. So here I have looks like a power of 3, a degree 3. It looks like a cubic. So it's certainly, I don't know if it's a degree 3 for sure, but I know it certainly is odd because I see it's up and then it's down. And because it's overall falling or decreasing towards negative infinity, I must have a negative leading coefficient. Okay, on the next page, some information about local extrema. A polynomial of degree n is going to have at most n minus 1 turning points or extrema. So for example, if a polynomial has or is degree 8, it'll have then 8 minus 1, or, excuse me, try that again, 8 minus 1 or 7. There we go, 7 extrema. A polynomial of degree 5, a quintic, will have at most 5 minus 1 or 4 local extrema. And then the zeros. If a polynomial is degree n, it'll have at most n real zeros. And remember that graphically, these are the x-intercepts. x-intercepts. It's hard to read. Try that again. X-intercepts of the function. If the degree is odd, the polynomial has to cross the x-axis at least one time. If we go up, down, or down, up, it's going to have to strike at some point right there. But if the degree is even, it actually doesn't have to cross at all. Think of a parabola. A parabola does not have to cross the x-axis. Same thing with a degree 4, a quartic might look like that, and it never crosses the x-axis. So now let's kind of put these ideas into practice as we conclude. Number 5 says, what would be the minimum degree of the polynomial whose graph is shown? Well, I see 1, 2, 3, 4 turning points, which means the degree would have to be a minimum of 5. So that looks like it could be a quintic. So degree 5, we call that a quintic. A possible equation of this polynomial is given here. And look at the degrees. I have an x squared, and then an x to the first. If I add up all those powers, we're going to get a total of x to the 5th. So there's my degree 5. Now the multiplicity concept, that's the last thing we're going to discuss here in this video. The multiplicity is essentially a repeated 0. So the multiplicity of a 0 is the number of times a 0 is repeated. The number of times a 0 is repeated. And we can check the multiplicity by looking at the power on each of the factors or each of the variables there. Okay. In this case, I would see this 0 would be x equals -2. The next 0 is x equals +2. And this 0 would be x equals 5. Just by looking at that factored form, I could extract the zeros. But notice that I would have a multiplicity of 2 for the first 0, a multiplicity of 2 for the second 0, and then that x equals 5 is just x minus 5 to the power of 1, so that's a multiplicity of 1 for that final 0. All right, so we'll end with this question here. Find the zeros and state the multiplicity of each. Well, looks like -1, +2, and +6 would be the zeros. So x equals -1, x equals +2, and then x equals +6. Now, with multiplicity, the connection to the graph will be just a little touch or kind of a tangent right there. If that happens, we have an even multiplicity. Often it's going to be a multiplicity of 2. So x equals -1 is going to have a multiplicity of 2. And I can see that right here by the power of 2 on the x plus 1. X equals 2. That's a complete crosses through. Try that again here. Stylus is sticking just a little bit. All right, there we go. Cross through the x-axis right there at x equals 2. It slashes through. It doesn't just kind of gently rest upon it and swoop away, but it slices right through the x-axis. And when that happens, we have a multiplicity of 1. Multiplicity of 1. If I go back to my function, the 0 of 2 right here just has a power of 1. So there's my multiplicity of 1. And look at this last one here, x minus 6 to the power of 3. So when we have this sort of plateau feature, a plateau feature where it kind of flattens out on the x-axis, but it still goes through. It's not a clean cut or a clean slice like it is back here at x equals 2. At x equals 6, we have this leveling off, this plateau feature at 6, but it still is going through the x-axis. That'll be an odd multiplicity of 3. So x equals 6 has a repeated 0 of itself 3 times. So by now, we should be able to see the connections between the factored form right here and the powers of each factor and how they relate to the multiplicity of each one of those zeros. And by the way, one last comment. This is a degree 6. That's a degree 6 polynomial. There should be 6 zeros accounted for here. And if I look back at my list of zeros, we might say that I have a -1 and then a 2 and then a 6. Aren't those 3 zeros? Where are the other zeros if I should have a total of 6? But remember, this -1 counts twice. So I have -1, -1, and then I have 2, and then I have 6, 3 more times, and there's my total of 6 zeros. So that's an introduction to finding key features and key characteristics of polynomial graphs and functions. That was a pretty broad overview. Feel free to pause and rewind or fast forward the video to help you in any way with taking notes on polynomial functions of any degree.